All right, so this series of lectures, we're gonna look at the electric potential diagrams. And when we talk about the electric potential diagrams, um, what we're doing is representing the electric potential difference between various locations in an electric circuit. Again, remember the positive terminal of the battery uh, as an electric potential that's equal to the voltage rating of the battery. So let me just go over the basic concept of the circuit. For you to have a circuit, you have to have a complete loop, a closed loop of, say, wires, and you need an energy source, a battery. What the battery does, the battery, the battery has a high potential terminal and a low potential terminal. What the battery or any energy source, if you take the electric energy at your house, all the company does when they provide you with electricity is to give you an electric potential difference. What they do is they move that positive charge from from the low potential terminal to the high potential terminal. That's all you're doing. And by doing that, you have an electric potential difference. You have an electric potential difference. And it is that electric potential difference which is going to now drive the positive charge through the wire to the negative terminal or the low potential terminal. It is similar to, say for instance, you're at a water park and you have the slide with the water and stuff like that. Or say you're at one of those amusement park and you have the coasters. The coasters have to get to, they usually start at some height and then they run down, they come down the tracks. For the coasters to get to that height, you need an external energy source to move it up to that height. You do not need any energy for it to come down. Gravity is going to pull it down. The same thing with electricity. You need a battery source to move the positive charge from the negative or the low potential terminal to the positive or the high potential terminal. Once you get the charge to the high potential terminal, you don't need the battery anymore because it's natural for that positive charge to be attracted to the negative terminal. Okay? So when we represent an electric potential diagram, we represent the electric potential difference between the various locations in an electric circuit. The positive terminal of the battery. So when you have a battery and it gives you the positive terminal is equal to the voltage rating of the battery. So if the battery is 1.5 volts, the positive terminal is 1.5 volts, and the negative or low potential terminal is 0. Okay? So you always remember that. The high potential terminal or the positive terminal is the electric potential of the battery. And then the negative terminal of the battery is 0 voltage. So if you have a battery, so in this situation, okay, you have a battery with 3 volts. This battery is 3 volts. What the high potential terminal is right here, the low potential terminal is right there. The high potential terminal is 3 volts, the low potential terminal is 0 volts. The potential difference, the potential difference is 3 volts, but the high potential terminal is the 3 volts, the low potential terminal is 0. Okay, and then you may have other electrical elements, circuit elements in the circuit. So you have to remember what the voltage is. As we say, is the electric potential difference. Okay, it is the difference in electric potential energy. And we define the volts, we define the volts as the change, the difference in potential energy, the difference in potential energy per unit charge. Okay, so the volt, the volt or the voltage is really joules per coulomb, because it is the change in potential energy with respect to charge. So you have to remember that what the volt is, because that's going to come in handy later on. So again, the volt or the voltage, which is the electric potential difference, is the change in potential energy. Energy is in joules per unit charge, and charge is in coulombs. So the voltage is joules per coulomb. Remember that. Again, when you have your battery in the circuit, so this represents the battery. Okay, this is the positive terminal, this is the negative terminal. The positive terminal is usually the voltage rating of the battery. So the positive terminal is 3 volts, the negative terminal is 0 volts. Again, what the battery does, it moves the positive charge. It moves the positive charge from the low potential terminal and it takes it to the high potential terminal. You are moving this positive charge towards a positive charge. And that is why you need energy, because the natural thing is for you to get repulsion. The natural thing is for you to get repulsion. Not only that, but you're moving a positive charge away from a negative charge. The natural thing is for you to attract it. So in order to overcome that attraction and repulsion, you need energy. Okay? And that is why you need a battery source. Okay? You need a battery source to move that positive charge from the low potential terminal to the high potential terminal. Once you move the charge to the high potential terminal, it will be naturally attracted through the circuit back to the negative charge, the low potential terminal, because it is positive. This is what we call the internal circuit. The battery is the internal circuit, and then the series of wires and stuff is the external circuit. The positive charge is going to move through your circuit because it's going to be attracted to the low potential negative terminal. Okay, so once you understand that, then you will appreciate how to draw these diagrams. So again, the battery energizes the charge to pump it from the low voltage terminal, low potential terminal, to the high voltage terminal, high potential terminal. Okay, that is what the battery does. You don't need the battery to do anything else. The battery establishes the electrical potential difference across the two ends of the external circuit. You need some energy source to establish that electrical potential difference. Sorry, the electrical potential difference. You need something to do that. And when you get a power supply at your house, that's all the company is doing. They're doing nothing more. They're providing that electrical potential difference so that the positive charge, because you're going to provide the wires and all that sort of stuff in your house. They don't do that. They're just going to give you the energy. They give you electrical potential difference. And once they get that positive charge moving from the negative or the low potential terminal to the high potential terminal, then the positive charge is naturally going to flow through the wire towards the low potential terminal. Okay? So the battery establishes the electrical potential difference across the two ends of the external circuit. Again, this is your battery. This is your external circuit. So you have the negative. We said the negative portion of the battery is the low potential terminal. The positive is the high potential terminal. What the battery is going to do is going to move the positive charge from the low potential terminal to the high potential terminal. It's going to move that positive charge away from this negative charge up to the high potential terminal. You need energy for that. And then once it releases the positive charge, it's going to naturally flow through the circuit back because it's going to be attracted to this low potential negative terminal. It is similar to your roller coaster ride at the amusement park. It is similar to your water uh, slides at the amusement park. You need energy to pump the water up to the top of the slide. The water is going to naturally flow down. You don't need any energy for the water to flow down the slide. Okay? The force of gravity is going to pull the water down. Okay? Similarly, all you need is energy to move your positive charge to the positive terminal. That's all you needed to do. The positive charge will be naturally attracted to the negative charge. So it's going to flow this in that direction. Okay, so the total. So we had talked a little bit about voltage drop, but when we talk about voltage drop, it is total the total voltage drop across the whole circuit is required to move the charge. Well, it's equal to the voltage to move the charge throughout the circuit. Okay, so the total voltage drop across the external circuit as the charge moves is equal to the battery voltage. So when we'll go over that again, but when we say voltage drop, in order to move this positive charge through the external circuit, in order to move it through the external circuit, right? So in order to move this positive charge through the external circuit and back to the negative, you're going to get what we call a voltage drop. So say for instance, this battery was 12 volts. When the charge moved from the high potential terminal to the low potential terminal, the voltage drop is going to be 12 volts. We'll get to that. Don't worry about that. So the total voltage drop across the external circuit as the charge moves is equal to the battery voltage. All right. Again, this is your battery, okay? That is your battery. What are the requirements for a circuit? What do you need for an electric circuit? You need electric potential. Again, electric potential difference. You need that electric potential difference. And what's going to give you that electric potential difference is your battery or your energy source. And then you need a complete loop of conductor, usually wires. So you need a complete loop of electric wires, and you need a battery source or an energy source. So electric potential is location dependent. It depends on where the charge is. Okay? If you have a charge closer to, let's go over that. So if you have a charge, so this is our positive terminal or negative terminal. Okay? When we say electric potential is location dependent, if you have a charge which is right here, say you have a charge right here, it's closer to your positive your high potential terminal. Okay, so it is going to, and it's a positive charge, so it's going to be repelled. It's going to be repelled by by your high potential terminal. So the charge here is going to be on a greater force because the distance is closer. Remember, we said that uh, when we talk about force, we talk about the 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 repulsion between your positive charge and your positive terminal. There's a force, a repulsive force. And remember that repulsive force is equal to K, the constant, times the charge, okay? The charge that's on your positive uh, on your positive terminal, divided by the square of the distance of separation, okay? Remember when we did our electric field diagrams? So the closer the charge is to the source, the the greater the energy, or the greater the potential uh, uh, energy. The greater the force, the greater the potential energy. So electric potential is location dependent, and we went over this. Okay. Um, so electric potential is the electric potential energy. So when we talk about electric potential, all we mean is the electric potential energy, and it is the electric potential energy per unit charge. So electric potential, okay, is the electric potential energy per unit charge, and that's what we call, uh, the difference. The electric potential difference is the volts. So the electric potential difference is the electric potential energy per unit charge. Okay? Electric potential difference is the change in electric potential energy per unit charge. Let me go back over this and let me draw it because it's very important. All right, so we have a positive source charge right here. Okay, and we say we have a positive test charge. Okay, now as you know, when you have a positive source charge, you're going to have your field lines, your electric field lines, which are going to be away from it. Okay, away from it. So the direction is going to be away. So your positive source charge is going to push your positive test charge away. It's going to push it away. Again, remember, the closer you get it this is our test charge. The closer you bring it to the positive source charge, more energy you have to use because the force that's pushing it away is K times Q, which is the charge on your source charge, divided by the separation distance squared. Okay? So the shorter the distance, the greater the force. So what we're saying, this electric potential, the electric potential on this test charge is location dependent. The closer it is, the more energy you have to expend to get it closer. So if it was way over here, less energy. So the electric potential is location dependent. Okay? The closer, the more energy you have to expend. So the electric potential difference, okay, is, well, so the definition for electric potential is the electric potential energy. So if I move this test charge close to this positive source charge, it's going to have a lot of electric potential energy. Okay? It is just like I lifting the water up to the top of the waterfalls. Okay, it's going to have more potential energy. Okay, but electric potential is defined as electric potential energy per unit charge. So whatever energy I expend to get it there, okay, divided by the charge, that's going to be the electric potential. Okay, all right. Now, electric potential difference is the difference in electric potential energy between the two locations. So that is the difference between this location and, say, we'll bring it closer to this location. Okay, so you're going to have an electric potential energy at this location, or let's call this location A. So you're going to have an electric potential. Again, electric potential is location dependent. Okay, so you can find out what the electric potential energy at this location, and then say we'll move it to a position B, which is closer to your source charge. So if we move your test charge to position B now, you have to use a lot of energy to bring it at position B, because it's now getting closer to your positive source charge. It's going to repel it. Okay, again, remember force. Force is equal to K, the constant, times the charge in your source charge, divided by the square of the distance. Since the distance is smaller, the force is going to be greater. You need more potential energy. You need more energy to bring it there. But once you leave it here, it's going to have more potential energy. So the electric potential difference is the difference in the potential energy between A and B. Because once you move the charge to B and you release it, it's going to be repelled. Remember, it's going to be repelled. So all that built up energy is going to, you're going to make use of it. It's going to be repelled. All right. So in order for you to have electric current flowing or charge moving, you need that electric potential difference. You need that. Okay, and that is what your battery does. All your battery do is to supply that electric potential difference. So what are the requirements for the circuit? You need a closed loop through which the charges can continuously move. You need a closed loop through which the charges can continuously move. You don't want the charge to move to a certain point and then there's a gap in the circuit and nothing happens. So you need a closed loop through which the charges can continuously move. And so once you have that, you're going to get the flow of charge within the circuit. So just think about it, just like if you go to your water park and you put your water on the top of whatever and you release that water, the water is going to flow down the slides. Okay? So the same thing, but you can't have any gap in the slide, because say you have a break in the slide, then the water is not going to flow to the bottom, right? So you need a closed loop through which the charges can continuously move. The flow of charge within the circuit is like the flow of the water coming down the slides. So the flow of charge within the circuit, so you need these things to occur for you to have a circuit. You also need the battery. You need the closed loop through which the charges can continuously move. You need the charge to be flowing within the circuit, and you need a battery. And we talk about the internal circuit. The internal circuit is the electrochemical cells or the battery, of the battery, or any energy supply. At your house, you don't have batteries. The electric company supply you with the energy. What they give you is what we call the electric potential difference. Okay? They give you the energy to move that positive test charge. towards the positive surcharge, or they move your positive charge towards the I potential terminal. That's all they do. Okay? So that is your internal circuit. The external circuit now is the part of the circuit where the charge is moving outside the battery or the energy through wires and light bulbs, etc. Okay, so that is your external circuit. So your circuit is going to have a battery or energy source, and then it's going to have your external circuit, which consists of wires um, through which you're going to use. So let's go over some questions because you'll probably understand it much better. So moving an electron within an electric field would change the, okay, so you have a number of things here. So you have an electron, so moving an electron within an electric field would change the what? Okay, the mass of the electron, the amount of charge on the electron, or the potential energy. All right, so let me just go over. So when we talk about a circuit, I'm talking about moving a positive charge to the I potential terminal to get that electric potential difference. I didn't talk about electrons or nothing like that. So you're moving your positive charge to the I potential terminal, and that positive charge now is going to move from your I potential terminal back to the low potential terminal. And then you're going to need the battery again to move it from the low potential terminal to the high potential terminal. Then it's going to travel through the external circuit back to the low potential terminal. You need the battery again. By convention, universal convention, the positive charge is going to move from the high potential terminal to the low potential terminal, which is negative. But the electron is going to travel in the opposite direction. Remember, the electrons are going to travel in the opposite direction. And, okay, and the electron is negatively charged. So the electron is going to move from your low potential terminal, which is negative, to the high potential terminal, which is positive. This is all by convention, universal convention. Okay? Remember what we said, I stress it. When you move a charge, the location of the charge, electric potential is location dependent. Okay? And remember what we say, electric potential is the electric potential energy per unit charge. So the electric potential, we say electric potential, but it's electric potential energy per unit charge. So when we move our electron within the electric field, all we're going to do is change the potential energy. The mass of the electron is going to remain the same. The amount of charge is going to remain the same. All we're going to do, so if we move, so if this was our electron, say this is our electron, which is negative, the amount of energy that it's going to have is going to depend on where it's located, the location. But by convention, we always talk about a positive test charge. So you can just think of the electron as your positive test charge. For us to move it anywhere, we're going to have to expend energy. So that is why the position or moving the electron within electric field, you're going to change the potential energy, because electric potential is location dependent. Okay, all right, the next question. If an electric circuit were analogous to a water circuit at a water park, okay, so the water circuit on the top of the thing, you have a bunch, there's some energy source that get the water to the top of the water park, then the battery voltage would be comparable to what? So if an electric circuit were analogous to a water circuit at a water park, then the battery voltage would be comparable to what? We need our battery. We need our battery. All our battery does is to move our, our positive charge from the low potential terminal to the high potential terminal. That's all the battery does. The battery supplies energy to move. The battery supplies energy to move that charge. So at the water park, what is comparable to that? Okay, so that will be comparable to then the battery voltage will be comparable to the water pressure between the top and the bottom, right? That's what the battery voltage would be equivalent to. So remember, your battery is going to move your positive charge from the low potential terminal, which is negative, to the high potential terminal, which is positive. So the water pressure between the top and the bottom of the circuit at the water park is equivalent. Your battery voltage is equivalent to that. All right. All right. If an electric circuit in your Walkman were analogous to a water circuit at the water park, so your Walkman, then the battery would be comparable to what? Okay. If the electric circuit in your Walkman were analogous to a water circuit at a water park, then the battery would be comparable to what? Okay. So your battery would be comparable to what? The pump that moves the water from the ground to the elevated position. That's what the battery does. Okay? The battery in an electric circuit moves the positive charge from the negative or low potential terminal to the high potential terminal. So at the water park, the pump moves the water from the ground to the elevated position. Same thing. Okay. All right. So which of the following is true about the electrical circuit in your flashlight? All right. So the first one said charge moves around the circuit very fast, nearly as fast as the speed of light. All right. So okay. The battery supplies the charge. No. The battery supplies the charge that moves through the wire. No. The charge becomes used up. No. The battery supply energy that raises the charge from the low to the. Okay. So the battery supplies the energy that raises the charge from the low potential terminal to the high potential. That's all the battery does. Just like the water park, the pump is going to pump the water up to the top. You need nothing more. The water is going to flow down by itself. Okay? All right. So if a battery provides a high voltage, it can do a lot of work over the course of life and do a lot of work on a charge. Then can push a lot of charge through a circuit. That's one. So it can push a lot of charge through the circuit. Okay, if there's a high voltage. Remember what the voltage is. Okay, voltage is joules per coulomb. So if it has a high voltage, so it's gonna push a lot of charge uh, through the circuit. Okay. it's gonna do a lot of work on each charge because it's the number of joules. So if it was, so it's gonna, sorry. So if you look at the definition of it, it's gonna do a lot of work on each charge it's encountered. So this is the correct answer because say you have five volts, it's gonna be 5 joules per coulomb. If you have 10 volts, it's gonna be 10 joules per coulomb. So it's gonna be more energy, a lot more work on each charge. Okay, so you just have to look at the formula or the definition for volts. Okay, all right, all right. The diagram below at the right shows a light bulb connected by wires to the positive and the negative terminal of a car battery. So this is a simple circuit. You have your battery, you have your internal circuit, your external circuit, and you have a light bulb. So use the diagram in answering the next 4 questions. So compared D to A, compared to point D, the A point is, so compared to D, so D is your low potential terminal, A is your high potential terminal. So the point A is, so this is a 12 volts battery. So this is your high potential terminal is 12 volts, your low potential terminal is 0 volts. So point A is 12 volts, so let's see, 12 volts higher, right? Because this is your high potential terminal and this is your low potential terminal. So your point A is 12 volts higher than point D. Again, it's your high potential terminal, low potential terminal. The high potential terminal is the voltage rating of the battery. Low potential terminal is 0. All right. So the electric potential energy of a charge is 0 at point. Sorry. So it is 0 at point D, right? Right? 0 at point D. Okay, this is your high potential terminal, voltage rating of your battery. Low potential terminal, 0 voltage. So the potential is at point D. Then this. Energy is required to force a positive test charge to move. So energy is required to force a positive test charge to move. Okay. So energy is required to move positive test charge from D to A. Remember, you're going to move your positive test charge from the low potential terminal to your high potential terminal. That's how you get your potential difference. And you need a potential difference. So it's going to move from D to A through the battery from point D to A. You have to move for before anything happens. That is why you need a battery to move the positive test charge from the low potential terminal to the high potential terminal. Okay, that's through the battery. So that's and then the energy required to move a 2 coulomb of charge between points D and A is, so let's go back. So this battery voltage has a rating of 12 volts. So in order to move, and this is the definition now. So 12 volts is equal to 12 joules per coulomb, right? That's what it is. So if you're going to move, so it's 12, so 12 volts means 12 joules per coulomb. So if you're going to move 2 coulombs, you have to, so let's look at the question. Sorry. It said the energy required to move 2 coulombs. So all you have to do is just look at the, sorry. All you have to do is just look at the definition. So 12 volts is equal to 12 joules per coulomb. So if you're going to move 2 coulombs, if you're going to move 2 coulombs, you have to, so it's 2 coulombs. So if you're going to move 2 coulombs, you have to move 12 volts all you have to do is look at the equation, the energy that you're going to need to move 2 coulombs. So voltage is equal to joules per coulomb. Okay? So in order for you to get the energy, which is joules, remember energy is joules, you just have to multiply the voltage by the coulomb. Okay? Because if you simplify this equation to get just joules, which is the energy, it is equal to volts times coulomb. So it will be 12 times 2, which is 24. So that's 24. Okay? The energy required to move 2 coulombs of charge between point D and A. Okay? Let me just go back and show it. Okay? So the voltage of the battery is 12 volts. The volt is defined as joules per coulomb. So 1 volt that. So if you simplify it and say coulombs is equal to joules, joules is equal to voltage times coulomb, right? Which is the energy. So all you have to do is multiply your voltage rating by the coulombs. So it is 2 coulombs and the voltage is 12. So it's 24. Okay? All right, so let's look at this one. The following circuit consists of a D cell and a light bulb. Okay? Use greater than, less than, and equal symbols to compare the electric potential at A to B and C to D. Indicate whether the device adds energy to or remove energy from the charge. So you have your battery source, you have your high potential terminal, your low potential terminal. Your positive charge is going to move like this. Okay? So it says, so what you're going to do, V to A. So the voltage at A and B. So we already know that this is our low potential terminal. This is our high potential terminal. So the voltage at A is 0, really. So it is less than B, because B is your high potential terminal. So the voltage at A is less than, because this is our low potential terminal, high potential terminal. This is actually 0, and this is whatever the battery voltage rating. So V, the voltage at A is less than voltage at B. What about C and D? This is C and this is D. Again, when you have a circuit element, it's going to remove energy. So any circuit elements, whether it's a motor, a bulb, anything, it's going to remove energy. So remember, what you're going to have electric potential energy. So you're going to have an electric potential difference. The battery is going to set up your electric potential difference, and it's going to cause the charge to flow through the circuit. This charge is actually electric energy. So electric energy is going to be traveling through the wire. It's going to give up some of its energy to the bulb. It's going to light the bulb, and you're going to have a little heat. So it's going to give up some energy, and then it's going to travel here, come back here, and then when it comes here, the energy is 0. It's give up all its energy. Okay, and then the battery again move the positive test charge there to get your electric potential difference. Then once you have electric potential difference, the charge is going to naturally flow, but it's going to give up energy along its way. So the voltage here is going to be greater than the voltage there, because you're going to have what we call voltage drop across here. Because, so C, the voltage at C is going to be less than the voltage at D. So less than, okay? And what about B and D? So this is D. So there is no element, there's no circuit element between B and D. There's going to be a slight loss of electric energy, but not much. So they're going to be approximately, if you want to say equal, then that's fine. They're gonna be, because you don't have any circuit element like right here between D and C. Between D and C, you have a light bulb. So this light bulb is gonna take energy. Because remember, your electric circuit just gonna supply energy. That's what it does. It supply energy. Some of the energy is gonna be taken out here. But between B and D, there is no element. You're gonna lose a little bit of energy, however, you know, probably in eat or something like that. Okay? All right. So, all right. All right, let's skip that. Let's take a break